In previous lecture, it was pointed out that there are certain processes, in particular the isothermal compression and isothermal expansion process, which is difficult to carry out or difficult to build a component which can carry out these processes. So the reverse Carnot cycle could be shifted inside the saturation dome, but again there are issues with wet compression and wet expansion. So in case of vapor compression refrigeration cycle, straight away from the evaporator pressure to condenser pressure, the process was carried out in adiabatic compressor. So because of that, you have some desuperheating here, and then the condensation process. 2-3 is the condensation process which occurs in a heat exchanger, right? The whole thing to 2-3, though the volume is decreasing, you are not using any moving component here, and you don't have the issue of providing a large area inside that with that moving component or fast moving machine. So you don't need to use any machine here. Any moving component is not there, and basically it's a heat exchanger, and still you are able to achieve the reduction in volume. So that's what happens in a condenser. And the next process in case of reverse Carnot cycle was again 3-4 but again it was wet expansion, and the work that you produce is not really very significant. So you like it's not practicable to use a costly device to recover little amount of work. So because of that, this process 3-4, the isentropic expansion was replaced in a vapor compression refrigeration cycle with process 3-4, which is isenthalpic expansion. In this isenthalpic expansion, a very simple component is required, and the cost of that component is also very less. But then because you replace that reverse Carnot cycle, you make changes with that, like going up to the condenser pressure from 2 to 2 on this path rather than 2 to 2 And another thing is, rather than going along 3-4 you are going along 3-4. So because of these two changes, as compared to this reverse Carnot cycle 1-2 3-4 there are certain changes that you have made, and this area is added. 2 to 2 area is added, which is area A1, and this increases the work inside the cycle. So this is an additional work that you need to put in the cycle to achieve this required effect of refrigeration. And another change made here is you are moving along 3-4 rather than 3-4. So if it were along 3-4, you would have got evaporation right from 4 to 1, but now you are getting it from 4 to 1. And as you know, the area below this process shows the refrigeration effect, the amount of heat that is accepted by the cycle or absorbed in the system. So that has now reduced. So the area of this rectangle was earlier 4-1 EC, but now the area is 4-1 ED 4, right? So the refrigeration effect produced in single cycle has reduced. So that is equivalent to area A2. So what is happening is, because of these changes, the COP of the cycle, the reverse Carnot cycle and the vapor compression refrigeration cycle, if you compare it, the vapor compression refrigeration cycle is supposed to give you lower COP as compared to the reverse Carnot cycle. So we will show that with a little.
Hello, sir.
With the help of this equation, right? You
I have
would
one
be able to
I have
realize that.
question.
Yeah. I would appreciate if you first raise your hand and then ask the question once I tell you to ask the question. As of now, you can go ahead. Yes.
Sir, why expansion from 3 to 4 days is not desirable?
Expansion. I think it has been explained. The expansion from 3 to 4 dash is not desirable. I think this was covered in the previous lecture. That 3-4 dash is what type of process it is. It is isentropic expansion. It is desirable, but that is a theoretical thing. It would be the work that you produce in that can reduce the net work, in the cycle. So it's desirable. But if you know the equation for the steady flow process carried out in this expander, the work that will be produced, theoretical work that will be produced, can be given by integration V dP, V specific volume, right? And dP is change in pressure. Okay, so that is written somewhere. Let me modifications, eliminating isothermal compression process, replacement isenthalpic. Yes. So this should be, yeah. So it's basically integration VDP and that V this specific volume, right? So the specific volume is very small if you are on the left hand side, the expansion process, as compared to the compression process. So compression process is having higher specific volume because it is dealing with vapor, but expansion process deals with most of the liquid where specific volume is much smaller, and dP is the change in pressure. So because of this, anyway you are not going to produce very large amount of work. And then wet compression again has issues. The hardware for that is not well developed. There could be like issues when you have liquid, dealing with liquid, and you want to do the lubrication, so it can interfere with the lubrication also, right? And there is expansion inside that fast moving machine. So expansion process, the specific volume changes like abruptly. So the hardware or the expander where this can be done could be a costly device. I'm not denying that it's impossible to do that, but it will be worth doing it if we were able to produce significant amount of work. That is not the case. So at least in small systems, it is not advisable to go for an expander. For large systems, it can be tried and you can recover some work. Like finally, you have to see what is the cost of the component and in how much time running period you are able to recover that, right? And the required R&D is you have to invest in that, and you have to develop that kind of component, right? So using an expander is not at all common in vapor compression refrigeration system. Rather, you are able to replace it with a very simple device, which is a throttling device. Okay, it can be as simple as you have uh, uh, like a curtain, and you make a hole in that metal curtain, and you make a hole in that, or metal plate, and you make a small hole in that. And on one side you can have high temperature or high temperature, high pressure refrigerant, and on the other side you can produce the low temperature, low pressure refrigerant, right? So this is the reason why it's not people have found that it's not worth doing it, at least in small systems. If you are very conscious about energy saving, and if you are able to produce or develop a device where this can be done, it would be worth doing it, right? But again, you have to look at the economical feasibility of that also. Okay, yeah. So now The COP of a vapor compression refrigeration cycle, if you compare it with the COP of a reverse Carnot cycle, both of them are shown together on this, right? So as you must have already understood that. So COP, in case of the vapor compression refrigeration cycle, the heat that is absorbed or the cooling effect that is produced, right? So because small q is written, you can understand that unit could be kilojoule per kg. So we are talking about a single cycle. How much cooling is produced in this process, 41 or 4-1, either of these two. So in case of vapor compression refrigeration system, it is 4-1. Right, it is 4-1 in case of vapor compression refrigeration cycle. And what is the net work that is consumed in that cycle, that will be put in the denominator. And now you are trying to compare it with the reverse Carnot cycle. So the reverse Carnot cycle is this 1 2 double dash 2 dash 3 4 dash 1. Okay. So if you compare it with that, what you find is that what is the change in cooling effect? You see that whatever was the cooling effect produced in the Carnot cycle or reverse Carnot cycle, it has been reduced by area A2. It has been reduced by area A2, right? Because there is a difference in area between the rectangle 4-1 EC and 4-1 ED. So what is that difference? We have given it the name A2 to that area. So that much cooling effect has reduced. And what about the work that is consumed in the cycle? The work consumed in the cycle has increased as compared to the previous one, the reverse Carnot cycle in case of VCR system. So this is area A1. So you can very clearly see this hatched area that has increased the area inside the cycle. So because of that, this additional area A1 is added to that. And if you carry out the energy balance, you will also find that the area A2 is also an additional thing which is there in case of the vapor compression refrigeration cycle, right? So because of this, you are able to show that the COP produced by the or given by the vapor compression refrigeration system is less than the COP of the reverse Carnot cycle. As you can see, the things written here, area D41ED is heat absorbed in the cycle, right? So probably it's not for this particular, because there is no, yeah, it's there. Okay, so D41ED, right, is heat absorbed in the cycle. We are talking about the vapor compression refrigeration cycle. Thus, reduction in cooling effect in cycle is equal to area E2 as compared to the reverse Carnot cycle. The heat rejected is equal to area E. Okay, this whole area E, then 2 dash 3, okay, CE, right, CE. So the whole area, okay, the heat rejected is equal to the area below this. So in case of VCR cycle, okay, E2 dash 3 CE, right? So that is the heat rejected in the cycle, vapor compression refrigeration cycle. This is higher than the reverse Carnot cycle by area equal to area of triangle 2 dash 2 double dash, right? 2 dash 2 double dash. That's the additional heat rejected as compared to the reverse Carnot cycle. Now the work done in cycle is equal to heat rejected from the cycle minus heat supply to the cycle. Thus, okay, heat supply to the cycle is this area, right? So what you find is, what is the additional heat rejected? It is equal to A1 plus A2. Additional heat rejected in vapor compression refrigeration cycle is equal to whatever is there for the reverse Carnot cycle plus A1 plus A2. That's the additional heat rejected. So additional heat means total heat rejected minus the heat that is absorbed, that would give you work. So what is the difference between those two? It's equal to whatever is there inside this rectangle plus A1 plus A2, right? So that is the additional means that is the total work that is consumed in the. If you compare these two cycles, the reverse Carnot cycle gives you higher COP and the vapor compression refrigeration cycle gives you lower COP. But there is no point in sticking to reverse Carnot cycle if you cannot implement it, right? So finally, you have to like move on and you have to accept whatever is the changes that you have to make. Otherwise, you cannot implement the system, particularly the way we want to achieve the things, right? That like we want high rates of flow. We want to carry out the compression and expansion in fast moving machines, which are compact machines, and there you cannot reject heat at a very high rate. So you have to accept the practical realities and you have to build your system accordingly, right? But like if possible, you would try to move that. So in future, if you can build such a technology, you will be able to make means increase the COP of the system. You will be making a positive change if you can do those kind of changes and build the required hardware for carrying out those processes. Okay, so now let us forget about the reverse Carnot cycle and accept vapor compression refrigeration cycle and start discussing about the analysis of the vapor compression refrigeration cycle, so that we can implement some real systems. We can take some readings, we can do some calculations, and we can get different performance parameters of the vapor compression refrigeration cycle. Okay, so the cooling rate would be one of the important thing, and COP would be the another important thing that we would be interested in. Primarily, like what is the rate at which you want to produce cooling, right? That is one of the important things that one would like to know. Or you are given a task to build a system which provides a particular cooling rate. For example, like when you purchase an AC, you are asked what is the capacity that you want, whether you want 1 ton of refrigeration or you want 1.5 or 2 or what, right? So similarly, you can have like different other applications and even much larger systems, or maybe some very small systems, miniature systems also. Okay, so cooling rate is one of the important parameters. We would like to get that. And another important parameters is the energy performance or the COP of the system, because you are consuming some power, and by consuming that, what is the cooling rate that you produce? The ratio of those two is the COP of the performance. So it's always desirable that with the same amount of power consumption, if you can build a system which can provide high rate of cooling, it would always be desirable. So let us do the first law analysis, that is first law of thermodynamics analysis, that is the energy balance, right? The first law of thermodynamics is nothing but the energy balance. So there are different forms of the first law of thermodynamics. Like for a closed system, there is a particular equation. If it is working on a cycle, you write it as cyclic integral of Q is equal to cyclic integral of W. And if you are talking about a process, you write it as Q is equal to delta U plus W. But for an open system, so now this analysis would be applied to individual components of the system. Now you already know about the four important components, or the four basic components of vapor compression refrigeration cycle. So one of them is compressor, the other one is condenser, then the throttle wall, and an evaporator. So we will be taking them as separate systems for this analysis. So in that case, they are all open systems. If you talk about compressor, then it is taking the mass of refrigerant from outside, it is compressing it, and then it is delivering it, or there is a discharge from the compressor. So it's an open system, and there can be heat which may be absorbed from outside, or it may be rejected to outside. So they are all open systems individually. As a whole, it's a closed system, but individual component, they are all open systems. So we will analyze them as open systems one by one, and we will be applying the steady flow energy equation. So here the assumption is that or whatever results we get can be used only if your system is in the steady flow steady state condition. So you know what is steady flow steady state condition. So with time the parameters are not changing. If you are talking about the mass flow rate, then there is no accumulation of mass in the system, right? Whatever the rate at which the mass is entering into the system, it's leaving at the same rate. And if there is work interaction, even that rate is remaining same. If there is heat interaction with the surroundings, that rate is also not changing with time. At any point, if you measure any parameter, whether pressure or temperature or anything, right, with space it may be different. It may be different at different points, but it will not change with time. So if you have installed your the sensor at any particular point, it will not change with time. In that case, you can say that the system has achieved steady state. And we are going, whatever analysis we do is for the steady flow system, steady flow steady state system. Okay, so this is the general diagram that you can draw for all the components. So this is the entry point, let's say 1. This is the exit point, let's say 2. This is your system, and there is this red line. You can call it the control volume, the border or the periphery of your system, right? And like the work and heat can cross that border, right? So this is the general diagram which can be used for any of the 4 components. Okay, and here the rates are shown. Sometimes you write them as rates, and sometimes you can also write it as just the property used in kilojoule per kg, right? So here it is kilojoule per kg into mass flow rate. So in that case, it will become watts or kilowatts. Okay, particularly in case of heat, and similarly in case of work or power also. If you write work, we generally write it as just small w in kilojoule per kg. If you write just heat, then it will be small q in kilojoule per kg. But if you multiply it with the mass flow rate, which is in kg per second, then it becomes kilowatt or watt, and so on. Okay. So what is a general steady flow energy equation? The steady flow energy equation can be written as, so inlet and outlet or exit. So HI plus C is the velocity. So this is the kinetic energy component. This is the potential energy component, GZI at the inlet, right? So here it's written as 1. Here I have written it as I inlet, right? Probably I have written it like I and E because when we draw the cycle, we are writing 1, 2, 3, 4 like this. So like for compressor, it's fine. 1 is entry and 2 is exit. But then for condenser, it will like 2 will be the entry and 3 will be the exit. So that to avoid that kind of confusion, I have written inlet and outlet. And the heat is assume that the heat is supplied to the system, right? It may be the opposite thing, but in that case, this will come out to be negative, right? This Q will come out to be negative. So this is in all of these will be in kilojoule per kg. All of these terms, the unit would be kilojoule per kg. And this is the enthalpy at the exit. This is the kinetic energy at the exit, specific quantities, and potential energy and the work. So work is done by the system, right? So that is the general thing that we write. If it is the opposite thing, that if it is consuming work like say compressor, then W will come out to be negative. So that is what you also learn in thermodynamics. Now refrigeration air conditioning is more of a practical science and technology. So like even if you write W, let's say it is 20 kilowatt, you may write W is equal to 20 kilowatt, or W, you can write capital W and put a dot over that, and you write it as 20 kilowatt. You are not going to write it as minus 20 kilowatt, right? Because you see, when you evaluate the equation, I'm not advising you to not to use that negative sign when you are doing the analysis, but finally when you write it, you are not going to write it, because when you say compressor, anybody in the field knows that it's going to consume work, it's not going to produce work, right? So in practical way, when you write, you are not going to write minus or something. As we proceed further, you will realize those things or understand those things, right? So in the above equation, I is for the inlet condition of refrigerant, E relates to the exit conditions, but in all of these components, the change in kinetic and potential energy are very small compared to enthalpy change, so they are neglected. Following equations may be written for various components of VCR system. Okay, so let's do the analysis of different components one by one. So this equation applied to the compressor. These equations are already derived in thermodynamics, but because we are going to use them, let us repeat those things. So in case of compressor, the kinetic energy and potential energy changes are negligible, right? They are negligible because it's a small device, and velocity, we don't deny, we are not saying that it will be equal to 0, right? But it will be the change in this, like Ci square by 2 and C square by 2. The difference between those two will be very small, not like could be fraction of a percent many times as compared to the other change. And the main change is the change in enthalpy. Hi and He, the difference will be very large. Okay, and normally we write, when you write it as an equation, generally you don't write 2 into 1000 here, right? Assuming that everything is in joule per kg. Even H is in joule per kg, but normally it is represented in tables. You'll see that it's written in kilojoule per kg, because joule per kg difference is the unit is very small. So rather than that, it may be more, you may like maybe more comfortable with the unit kilojoule per kg. So when you evaluate this, you have to make sure that you divide it by 1000, whatever is the VI square, if other things are in kilojoule per kg. So generally, if you can recall the calculations done in thermodynamics, that these changes could be very small fraction of the change in, let's say, enthalpy in case of compressor. So you are able to, and it's a small device, so potential energy changes are very small. So we're going to neglect these terms, the kinetic energy change and the potential energy terms. And what about the heat? What about the heat? Right? It is already told that these devices are compact devices, fast moving machines. They don't provide very large surface area, though it may be desirable that they reject heat at whatever rates possible. So like the air compressors, if you have observed, they provide fins over that, right? Or in case of multi-stage compressor, you go for intercooling. So it may be a good idea to reject heat, but then again, most of the times that may be a very small part of the change in He minus Ho. As compared to that, these quantities may be very small. So many times you're able to assume it as an, and again in VCR cycle, we have assumed it to be adiabatic compression, right? Or isentropic, so reversible adiabatic compression process. So according to that, Q is equal to 0 as compared to the assumptions built in that cycle. So Q is equal to 0 in that case. So finally, for compressor, you are able to write W is equal to H2 minus H1. I'm writing everything in lowercase letter, and the unit is kilojoule per kg or joule per kg. Now, if you talk about the condenser, what is a condenser? It's a heat exchanger, right? Now, in heat exchanger, there is no work done, and there is little change in the kinetic energy and potential energy also, right? Or it's small as compared to, again, enthalpy change. We are not saying that it's equal to 0, right? But the change is very small as compared to the change in enthalpy, right? And if you might have already solved some example and already realized these things. Okay. So we don't want to unnecessarily complicate the calculations and probably waste time on that. And that's why we are simplifying the equation as much as possible so that you can do the calculations quickly. Okay, so H2 minus H3, that is the condenser work. Now, as you might have seen, like this W, if I take this HE on the other side, it will be HI minus HE. Right now, which one is bigger? HE is bigger, so W is going to come out negative, right? W is going to come out negative. Okay, but what I have written here is, though I have written H2 and H1, if I follow this equation, it will be HE minus HI. Sorry, HI minus HE, which will be negative. But I have written actually HE minus HI, which will be positive. So I just want the number, right? I just want the number, and I know that it's going to consume work, right? So the equation is written that way. Okay, so you can observe that we have not paid attention to the fact that whether it will be negative or positive. We already know it. We just want the number here, right? So it's written as H2. So higher minus lower. That's what it is written. Almost in all cases, or maybe in all cases, right? So H2 minus H1 is the enthalpy change, it is equal to the work, so kilojoule per kg. Then the heat rejected in the condenser QC is equal to H2 minus H3, again higher minus lower, right? H2 will be higher and H3 will be lower, right? Let's keep the cycle in front of us, right? I have not talked about the pH diagram. Probably I can also explain you pH diagram now. So your compression process, I'll show the actual pH diagram also, but as of now, just try to understand the things from here. So the compression process is isentropic, as seen in the TS diagram. The isentropic line on pH chart, pressure enthalpy chart. The isentropic lines are like this. They are slant lines, actually not exactly lines, they are curves, but it is shown as a straight line here. The curvature is not too high also for a small change as compared to the whole range of the chart. So 1, 2 is isentropic line, and then next process is condensation. So it's constant pressure, it's constant pressure, right? It's a constant pressure process. Up to 2 dash is not constant temperature. After 2 dash up to 3, it is constant temperature also. 2 dash is desuperheating, right? Okay. So it's constant pressure, so it's a horizontal line here. And this also shows you the nature of isothermal lines on the pH diagram. So if you draw this, the constant temperature line here, inside the saturation dome, it will be horizontal line. But in this portion, that is on the left hand side, on the liquid side, it will be a very steep line. It will be a very, not exactly vertical, but it will be a line with a very steep slope, right? Close to 90 degrees. And on the right hand side, in the vapor portion, superheated vapor portion, it will drop rapidly like this. That's the constant nature of constant temperature line on the pH diagram. Yeah. So this is condensation process. It comes out as a saturated liquid here. And now the isenthalpic expansion. So enthalpy, the x value remains constant. The pressure decreases. And you can see the temperature has also decreased from condenser temperature to evaporator temperature, right? So this temperature has, you can see this temperature, TE, the constant temperature line, this vertical, nearly vertical line, then becomes horizontal here and drops like this on the right hand side. Okay. So 3,4 is isenthalpic expansion in the throttle wall. It is a vertical line and again a horizontal line because the pressure and temperature remains constant here in the process of evaporation 4,1. And again then the compression process. Yes. Yes.
Sir,
Guru Panchal.
process. Yes, sir. Sir, is it 3 to 4 process is reversible or irreversible?
There is some noise from your side. Can you type the question and post it? Please type the question and post it. I hope you people are able to type the question. You have the comment box, right? So you can use the comment box. Okay, so by the time you are able to do that, I will. Yeah. So is throttling process reversible or irreversible? Yes. Throttling is an irreversible process. Right? Throttling is not a reversible process. So as I also told in the previous class that when I draw this diagram, I generally draw the process. I generally draw the process as a dashed line. Right? Generally draw the process as a dashed line. Okay. I believe the question was asked to me, so I answered that question. So that process is irreversible. Throttling is never a reversible process, right? You know how throttling is carried out, right? If you look at this, like you have a porous plug, and there is high pressure, high temperature fluid on this side, and there is low pressure, low temperature fluid on this side. Now, once it goes from this side to this side, you cannot reverse it, right? Without consuming some work, without some external influence, you cannot reverse the process. So obviously throttling is irreversible process, right? Isentropic expansion is a reversible process, but we have not been able to carry out that, and that's why we have implemented the vapor compression refrigeration cycle. Okay, yes. So I hope this solves the query, right? So H2 minus H3, that's the condenser QC, the heat rejected in the condenser, right? H2 minus H3, again higher minus lower, right? So if you look at this, H2 is higher. If you look here, look at here, then this is H2 and this is H3. So obviously H2 is higher than H3. So that difference is nothing but the the heat rejected in the condenser. So that's about the condenser. Next component is the throttle wall. Now in throttle wall, you will say that everything is zero, right? Means the change is zero. Kinetic energy change is very small, negligible. Potential energy change, anyway, it's a very small device. It is nearly zero. It's a very small device, very small surface area. So heat exchange is also non-existent and it's not supposed to produce any work, right? So finally HI is equal to HE. That's the equation that you get, right? And you feel that it is why this kind of equation should be there. But then you will find that still it is an important equation with the help of which we can solve the numericals. Right, so H3 is equal to H4. That's what you are stating when you do the energy balance for the throttle valve. For the evaporator, again similar to condenser, right? So the heat absorbed by the evaporator is equal to H1 minus H4. Again, we have done higher minus lower, right? So H1 is higher and H4 is lower. So this is H1, this is H4, right? H1 is higher, H4 is lower. So H1 minus H4. So we have written all positive like equations written such that they give you positive number, but you know that compressor is going to consume work. You know that the condenser is going to reject heat. You know there is no enthalpy change here, and you know that the evaporator is going to absorb or the system is going to accept heat, right? So four very simple equation, simplified forms of steady flow steady state equation are to be used in analyzing the standard or ideal vapor compression refrigeration cycle. And now COP is equal to QE minus W, right? So that's how you can get COP. And I have already introduced you the pH chart, and you need property tables. And with the help of that, you can get enthalpy. Enthalpy is the most important property, I think I would say, in the subject of refrigeration as well as air conditioning. Right, so we are most of the times concerned about the change in enthalpy. That gives you the total heat change. So the tables help you. Once you cannot measure enthalpy directly. Once you measure the measurable parameters, you are able to get the enthalpy change, right? So that's what will be one of the important exercises, getting the enthalpy at the given state. And once you get that, you can evaluate the performance. So how can you get the cooling rate? Like you have H1 minus H4, which is QE. Right? This is nothing but QE. H1 minus H4 multiplied by the mass flow rate of refrigerant will give you the cooling rate, and that will be the unit would be kilowatts. And you are interested in that number. What is the rate of cooling provided by your system? Compressor work, compressor enthalpy change is H2 minus H1 multiplied by the mass flow rate of refrigerant, right? And then compressor displacement is VC. I have written capital V, put a dot over that, and for compressor, so VC dot is equal to, this is specific volume. VR is the specific volume of refrigerant at state 1, right? State 1 is the entry to the compressor. State 1 is the entry to the compressor. So get the specific volume here, which is nothing but VG, right? VG from the steam tables, if you're using water, or the property tables, if you're using, it is that is the specific volume that you use here, VR, okay, and multiplied by the mass flow rate of refrigerant. So that this gives you the theoretical compressor displacement rate in meter cube per second. That is also one of the important parameter from point of view of like design of the compressor. Okay, so let me also show you the nature of the pH chart, and we are going to use it in the example. So next thing what we are going to do is solve an example on the ideal or standard vapor compression refrigeration cycle. Right? So let me introduce the pH chart to you. So I have actually put it on this. Let me see if this is better. So this is the saturation dome on the pH chart. This is pressure, enthalpy, pressure in given in megapascal, enthalpy in kilojoule per kg, and this is log scale. For pressure, it is log scale. Here it is linear scale for enthalpy, but pressure, so it's a semi-log chart. Okay. And this is the saturation dome, shape of the saturation dome. So on the left hand side, you have the saturated liquid. Here you have liquid plus vapor, and here on the right hand side, you have on the right hand side, you have the superheated vapor, right? And this is the enthalpy, as I told. There are other like constant. We talked about the isentropic line, right? So isentropic lines are moving like this. You can read here S is equal to 2.30 kilojoule per kg Kelvin. So that is an isentropic line, right? Constant entropy line. This is 2.2, this is 2.1, 2, 1.9, 1.8, right? And 1.6 here and so on. So this chain line is isentropic line. Okay. Then this constant temperature line, you can see this thing here, T equal to minus 10 degrees Celsius. It's a horizontal line, right, inside the saturation dome, but it is very steep line here, minus 10. You can read it again here, right, minus 10. And then on the right hand side, it drops like this, right? It's minus 10, then this is 0, then 10, 20, and so on. So if you take, let's say, this 40 line, it's moving like this, right? Then horizontal here and then nearly vertical here, right? So that is the constant temperature line on the pH chart. And some other properties are also seen, like specific volume is also available in this. Density 500 kg per meter cube, that is what is shown, but that is shown, density is shown only outside the saturation dome, not inside the saturation dome. Okay. So this is the pH chart, and many times we show the cycle on the pH diagram. This TS diagram is good for understanding the processes, but pH diagram is more commonly used for plotting the cycle, right? Because you already have the skeleton, the required lines are already there. You don't get such a TS chart, right? You get pH chart only. And on pH chart, you can plot the cycle, and the cycle also looks very simple there, right? Three of the processes are horizontal and vertical lines only. Only one process of isentropic compression is it moves on a curve, right? So